now what we're going to do is we're going to do lecture 3, which is the third lecture in our 3D statics topic so far. And now we're going to introduce is this idea of 3D moments. So what's the plan for today? In our third lecture, we're going to talk about what in the heck is a cross product, and we're going to do some example problems. Now let's start off in a very simple way. Take out your hand and put your hand in front of you and make an L. Haha, you just called yourself a loser. I'm just kidding. But take the L. What I want you to do is move your thumb forward. What you probably can see now is maybe only your index finger pointing up. But if you rotate your hand towards yourself, you'll again see the L, and both your finger and your thumb will be in the same plane. What you might do is bring your hand back to the same orientation as is shown on the screen and move your pointer finger down so that it's next to your other fingers pretty much. If you then rotate your hand upward so that your knuckles face you, you will still see an L. So something that this kind of is showing you is that no matter what you do, if you take one finger from your left hand and one finger from your right hand and you put them next to each other, you will always be able to rotate your hands such that those two fingers are in the same plane. So what essentially this means is that if two vectors, since they will always exist in the same plane, this means that there must always be a third vector, shown in this picture in purple, that is perpendicular to both of those vectors. This is usually called the right hand rule, which essentially if you put your thumb out to the side, your index finger up, and then you point your middle finger out, your middle finger is perpendicular to both your thumb and your index finger. So, the cross product essentially is the mathematical version of this, and you can see this represented in the little GIF that I found at Wikipedia. So what you can see is that we have a red vector and a blue vector, and the idea is that these two vectors will always be in the same plane. Now, if we have a red vector and a blue vector that are perpendicular to one another, we will have a third vector in purple that will exist, and this is called the cross product. And you can see that represented in this little GIF right here. So when the red arrow and the blue arrow are perpendicular, you will have a purple arrow that goes and is perpendicular. And as red and blue become less perpendicular, the purple arrow shrinks and goes down. So what you might realize this is kind of explaining is moments. So what the heck is the cross product used for? What we were just discussing is that if two vectors can always be in the same plane, then we can find a vector that is perpendicular to both of them. This is moments. So, remember from earlier in statics that we said that the moment, or rotational force, is equal to the perpendicular component of force times distance. So here's an example. Let's look at this beam that's supported by a pin at A and a roller at some unknown spot on the right. So if we've got a force in the y direction pushing down that's perpendicular to the beam and it's some distance away from x, we know that that force times that distance is going to cause a moment about point A. Well, that moment is in the z-axis, which is the axis that goes into or out of the board. And effectively, that's exactly what we're talking about. So if we get our highlighter out here, I can show you that effectively, let's make sure, no, I have my pen. So if we have the highlighter here, the force in the y direction is essentially our red arrow from above, and our x distance is essentially our blue force, or arrow. Then, our moment is essentially a force along the z-axis. Now this is going to be true for all three dimensions. We're going to have the following. So forces in the x and the y are going to cause moments about the z-axis. Forces and distances in the y and z are going to cause moments about the x, and forces in the z times distances in the x are going to cause moments about the y, or vice versa. So let's look at how this plays out in an actual better visualization in 3D. So in 3D statics, let's say that we have this force up here, FAB, and it's being multiplied by this moment arm right here, r. Well, you can already see that FAB is essentially going to be this part of our moment equation right here. And then our radius is going to be this part of our moment equation right here. Well, if we look at our force in the F direction, it's going to have an X component, a Y component, and a Z component. And unfortunately, our radius, or our moment arm in this particular case, is going to have an X, a Y, and a Z component as well. So just imagine trying to take all of these different things and multiply them together to get a moment. It might seem a bit overwhelming, and that's where we have the cross product come in. Now the cross product essentially must be in this order right here in order to work. This is very important that you have to do R cross F, otherwise our sign conventions will be a bit off. But the idea is that you have the moment arm, R, be in the top portion of the cross product, and then you have the force down in the bottom. That's going to be the other part of our cross product setup. So essentially we're just setting up this simple matrix, and we'll arrive at all of these things that go into this matrix here by looking at kind of all of the stuff that we've done so far up to this point, creating unit vectors, solving for forces, things like that. So what happens in the cross product is that we get this. So what you can see happening, and let me kind of erase what's going on for a second so it becomes more clear, is that when we have moments about the x-axis, that's going to be this section right here. Now where does this come from? Well, moments about the x are going to be caused by forces in the z direction times distances in the y, which is exactly what we see right here. We also can have moments about the x-axis by having forces in the y direction multiplied by distances in the z. That's this equation right here. The same is going to be true throughout, and going back to what we initially even talked about just a slide ago, was that forces in the z can be caused by our y force times an x distance. That was the example I just showed a second ago, minus forces in the x direction times distances in the y. So you can kind of see what's happening in the cross product, and the reason it's called the cross product is because we are making these crosses, or x's, when we're doing our multiplication in our table. So it's important to recognize that the cross product, if done in the wrong order, will give you the wrong sign. And this is important that in statics we might get messed up when we start to do the sum of the forces. The other thing you can realize is that I cross I is equal to j cross j is equal to k cross k, which is equal to 0. Which essentially, this is saying that a force in the x direction times a distance in the x direction will not cause a moment, because through line of action that goes through the point, right? So for example, if we had this point right here, and we had a beam coming off of that point, like that, if we had a force right here going into that point, and we were summing the moments about A, this force here would not count because it goes through that point. So the cross product only works for things that are perpendicular, which is why we're doing, in this case, x and y, y and z, or z and x. So forces along the direction of the moment arm do not cause a moment, which is why that bottom box is true. So now let's look at this particular example problem, and we'll apply the cross product along with everything else we've learned to solve for our problem. Now in the end, what we'll find is that our answer is the following. And as a way to kind of help you visualize what we're going to try and do, we're going to try and set up our cross product, and the way that we try and set up our cross product is by we need to first figure out R of OA and FB. And to visualize what's going to be happening in our cross product is we will be multiplying together things that are across from each other, And when you come back and look at the slides after we've discussed the solution, it'll become a lot more clear kind of the methodology that we're using to solve this problem. Now let's go to the handwritten solution and figure out how to approach these problems. Alright, now in this particular problem here, we're asked to solve for the resultant moment produced by forces FB and FC about this point down here, which is point O, which is our origin point. So you might have guessed it, but point O is going to be 0, 0, 0. That's where everything is originating from. Now if we look at force FB is directed from A to B down here. And force AC is directed from here down to the bottom over there. We're given the value of both FC and FB, and we're given the dimensions of all the different parts of our problem. So we're told to express our answer in terms of the unit vectors I, J, and K. So we've got a lot going on in this problem, and now we're going to introduce the idea of cross product and figure out how that works. So again, the way that we're going to approach this problem is the same that we approach every single 3D problem. So step number 1 is going to be to identify the important points of the problem. So establish the points. In this particular problem, the points that are going to be important are going to be A to C, because that's a tension, A to B, because that's something, and A to O, because that's our moment arm. So the points that we're going to need are A, B, C, and O, which, no surprise here, those are all four of the letters that are actually defined in this problem. And something that we can see in this problem as well is we have a z-axis this way, a y-axis this way, and an x-axis this way. So, establishing the points, we'll look at point A first. To get point A, we can see that it starts essentially at the origin. We only have to go up by a value of 6 meters. So A is going to be equal to 0, 0, 6. If we look, we're going to have B as well. If we look at B, B is on the ground. It's this like point right here that the cable is attached to. It is 2.5 meters this way in the Y, and it looks like it's on the axis over here. It's on the Y-axis, so that means that basically it doesn't have any X. So if we look at point B, that's going to be 0, 2.5, 0. If we look at point C, what we're going to see is 2 meters in the X, negative 3 meters in the Y, and 0 in the Z. And if we look at point D, which doesn't exist, unfortunately, I'm at point O. If we look at point O, that is our origin. That is point 0, 0, 0. So we've got everything we need. Step number 2 in all of our questions is always to figure out the vectors and magnitudes of all of our important stuff. Now in this case, we're going to have 3 important things to solve for. Because we have AC, AB, and we're also going to have O to A, which is from the point of rotation to the applied force. That's going to be important to recognize. So when we set this up, remember that AC is found by taking C minus A. That's 2 minus 0, negative 3 minus 0, and 0 minus 6. So this gets us a value of 2i minus 3j minus 6k. And when we take the magnitude of AC, we get a value of the square root of 2 squared plus 3 squared plus 6 squared, which is equal to 7. And we repeat this process for AB. We know that AB is going to be equal to B minus A, which again, reason we're doing this is because these are tensions. We're going from point A to B. That's the only way that this rope can pull. And over here, we're going from point A to C, which is the only way that that rope can pull. So when we do B minus A, that's going to be 0i, 2.5j, negative 6k. So we get 2.5j minus 6k. And by using the exact same methodology from above, we get that AB is equal to 6.5. Then what we'll do is we now take OA. And the reason we're doing OA is just because we want to go from the point of rotation to where the forces are applied. So when we look there, we're only going up. So we've got O to A is going to be A minus O. So effectively what we're going to get is 6 minus 0, 0 minus 0, and 0 minus 0. So this basically is going to get us here 0i plus 0j plus 6k. And our magnitude of OA, don't really need to do anything special here. It's just 6. Step number 3 in our problem now is going to be to solve for the unit vectors, which again we can kind of combine with the force vectors. But I'll just write out the unit vectors because I think we have some space on our page. So the unit vectors that are important in this one right here are UAC. And UAC is going to be equal to, remember, 2 over 7 minus 3 over 7 minus 6 over 7. So we have 2 over 7i minus 3 over 7j minus 6 over 7k. We'll also do that same thing for unit vector of AB. And for AB, we're just going to have 2.5 over 6.5j minus 6 over 6.5k. Now, step number 4, which sometimes we combine with step number 3, is our force vectors. So when we write the force vectors out, we really only have 2 of them. It's going to be the force of AC, or tension AC, and that is going to be equal to basically tension AC magnitude times the unit vector of AC. So that's what we just wrote up above. We've got TAC here. And now what we also are going to have is the force of AB is going to be equal to tension AB times the unit vector of AB as well, which is what we have up above. So remember, in the previous problems, we were trying to solve for TAC and TAB, but in this case, these are given. So we're not solving for those. And we have the unit vectors already. The thing that we're going to be trying to figure out is more or less, what is the moments? So how do we go about doing that? So before we move on to doing that, let's just write out what our force vectors are, just so we're all on the same page. So we know that the value of tension AC is given as 420, and we know that the value of TAB is given as 780. So FAC is going to be equal to 420 times 2 over 7, which gives us 840 over 7i, minus 1260 over 7j, minus 2520 over 7k. And if we look, we have force AB, which is going to be equal to 780. So let's just write that up here so we don't forget. And you know where these numbers are coming from. But it's going to be 780 times 2.5 over 6.5. So the value we get over here is 1950 over 6.5j minus 4680 over 6.5 K. Now these are our two forces that are going to be causing moments about point O, which that's the question we're trying to solve for. Now, just using common sense, we can see that our moment arm is in the z-axis. Therefore, this force right here in the z direction is not going to cause a moment because it goes through the moment arm. It's parallel. This same thing is going to be true about the z component of AB. This is not going to cause a moment either. The only ones that are going to cause a moment, which I'll do in green here, are the x components and the y components. Essentially, k cross k is going to be 0, but we can do I cross k and j cross k to get numerical values. So what we can see coming on right here is we've got three things that are going to cause a moment about point k, about the z-axis and the moment arm OA. So step number 5 is to solve for the moments with common sense, or essentially the strategies we've been using in the past. So the way that we can kind of figure this out is that only forces in the x and y can cause moments about the z. So if we look at it, what we can see is that the moments caused by force B, or moments caused by force AB about point O, are going to be only this component right here, times 6. And the moments caused by FAC are going to be these two moments. So essentially what we have to do is we have to sum up kind of what's happening here. So if you look, the moments about the y-axis, so if we sum the moments about the y-axis, that's going to be essentially either forces in the x times distances in the z, or forces in the z times distances in the x. Now this case doesn't exist in our particular problem, but we do have an x force and we do have a z moment arm. So the x force in our particular problem is 840 over 7 times the distance in the z direction, which is 6. And if you look at the answer to this, the moments about the y are going to be 720 Newton meters about the j. If we then look about the sum of the moments about the x-axis, the sum of the moments about the x-axis are going to be caused by forces in the y about moment arms in the z, or forces in the z multiplied by a moment arm in the y. Again, this doesn't exist in this particular problem, but we do have two y forces and a z moment arm right here. So the sum of the moments about the x-axis is going to be equal to negative 1260 over 7 times 6. This gets us negative 1080. And we also have the other component here, which is 1950 over 6.5 times 6. That's going to get us 1800. When you add these two things together, you get that the moments about the x-axis are 720 Newton meters in the I direction. So that's pretty much the answer to this question. that the moments are 720 Newton meters about the J and 720 Newton meters about the I. Now, if you got a little bit confused, I'll set up the cross product and you can see how that would play out. All right, so now what we're going to do is we're going to take our values from step 4 for force of AC vector, force of AB vector, and our moment arm OA vector, and we're going to set up some cross product equations. Now to solve this problem, we need two cross products. We need the cross product of ROA cross FAB and ROA cross FAC. Now, let's set these up. So let's do ROA cross FAB. The way that we set this equation up is going to be the following. We draw our cross product box, I, J, K, and we plug in our three values. In this case, we have 0, 0, 6 for ROA. And on the bottom, we have 0, 1950 over 6.5, which is right here. And then we also have negative 4680 over 6.5. Now, let's label this row U and this row V. And each of these columns is essentially column 1, 2, and 3. And usually it's fairly helpful when you're doing the cross product to write column I again over here. Now, the answer to the cross product is going to be equal to the following format. U2 times V3 minus U3 times V2. I plus U3 times V1 minus U1 times V3. J plus, so if we could squeeze it in over here, U1 times V2 minus U2 times V1. Okay. Oh yeah. Perfect fit. Okay. So essentially what we're going to do is we can look here at our cross product and we can realize that not much is going to happen. The only spot where we have any numbers in column V are here and here. So we've got V2 and V3. So we can kind of look at our equation here and see that, okay, we've got V3 and V2. We've got a V3 right here, and we've got a V2. So the only things that might matter to us here are this whole first one, this one, and this one. The other ones you can see are going to be 0 because look at all these zeros. Pretty much the only things that are going to multiply, if we do K cross J right here, we do 6 multiplied by this number right here, and our like little peanut looking thing, that would be U3 times V2. So that's this one over here. So let's just color this one with black right there. So the equation we get right here for this one is U3 times V2, which is equal to, it's negative by the way, because see how it's negative right there? So we have negative U3 times V2 is negative 6 times 1950 over 6.5. And what this is going to get us is a value of 1,800 I. Now the only other spot where we have a number is right here, 4680 over 6.5, but we can see in the cross product that would be multiplied by 0, so that's not going to matter at all. So we just leave this the way it is, and we leave it as 1,800 I. Now what we can do is we can set up the cross product of ROA cross FAC. I'm going to write that down on the paper so we can jump ahead and I'll explain what I've written. Okay, now what you can see is that I've written out the cross product setup, and again we have columns 1, 2, and 3. Effectively what you can see now is that I've got ROA still, and I've now plugged in the values for FAC down at the bottom, which we have right here, I, J, and K. And I've also again put this I column. Now something you can see is going to happen is that again we're going to have this K cross J just like we did in the last problem, which again is negative u3 times v2. Now in this particular case, we get negative 6 times negative 1260 over 7. Well, what does that get us? That's going to get us a value of 1260 over 7 times negative 6 gets us 1080 I. And we'll see how these two things are going to combine in a second. The other thing that we get out of all of this is we get that 6 times 840 over 7. Well, what is that? That's u3 times v1. Well, just to make things a little bit easier to see, that would be this thing right here, u3 over v1. So if we color this little peanut in blue, we can see that it's going to be a positive value. So we have u3 times v1. In this particular case, that is a value of 6 times 840 over 7, which gets us a value of 720 J. Kind of the final step in this whole problem, and I'll do it right up here in this little bit of space that we have left, is to sum all of the moments together. And the sum of the moments about O total is essentially ROA cross FAB plus ROA cross FAC. So what we get in this is that we have negative 1800 I minus 1080 I plus 720 J. Therefore, the sum of the moments about O, we will add these two components together. Sorry, this actually should be a plus. And what we'll get is that we get negative 720 I plus 720 J. And that is our final answer, which actually matches the answer that we came up using common sense before. And just to kind of explain this, if you look at FAB, for example, FAB is directed along the y-axis. Since that's on the y-axis, it's not going to cause this flagpole to rotate relative to the y-axis, which would be this way. So that's why when we do the cross product of FAB, the only thing that it's causing the flagpole to do is actually to rotate about the x-axis, kind of going like, and if this is our flagpole, it's going about the x-axis, but it's not going about the y-axis. That's why here, this cross product gets us negative 1800 in the I. And the reason it's negative is because that negative is causing it to rotate clockwise or forward about the x-axis. If we look at the force FAC, what that's doing, FAC is pointed in the opposite direction in the y-axis as FB, so that's going to cause this thing to rotate that way, or counterclockwise around the x-axis. That's why we get positive 1080 I. The other thing that we can see that's happening is that FC is located some distance away from the y-axis. Therefore, that's going to cause our flagpole to rotate around the y-axis counterclockwise, which is why we get a positive 720 over here. And that's what's going on in this problem and how you apply cross product to solve things. Now, in this particular example, as you saw just a page ago, I was able to figure things out just with common sense. And the reason why that's the case is because our moment arm was only a z moment arm, which is very simple. It's going straight up and down. So it's pretty clear that, hey, only certain forces, which are basically forces in the y and the x, are going to cause moments about moment arm in the z. But in the future, it's very possible that your moment arm might have a value in the I and the j, in which case it's going to be basically impossible to do unless you set up the cross products in such a way. And there you go. That's how you do cross product to solve for the moments caused by three-dimensional forces about a three-dimensional moment arm. Now, if you still have questions about cross product, I recommend you go back to the slides and look more closely at the final slide to see kind of another way to kind of visualize where all these things are coming from. And there's also an additional problem at the end with a solution that you can apply to check your work and see if you're getting cross product and understanding things. But that's it. And I want to end the video at exactly 10 minutes.
Man, I love 2D statics. Cables, beams, trusses, frames and machines. They're all just so great. But I guess I just wish there was more. Whoa! What's that? Whoa!